Alright, so talk about the gas chapter, guys. I mean, it's more of a gases and phase change. Okay. All right, so gases. So let me be straight here, guys. You know, so this chapter, gases. So students struggle with this chapter because I think the struggle with this chapter, guys, is like calculation. Okay, so there is a math portion here. Okay, and that's where the struggle is for some kids. Okay, so let's take a look at what this chapter is about. So. Oh, they're testing my patience. Oh, all right. So, PDRT. All right. So PDRT, guys. So this chapter, guys, revolves around this equation, PDRT. Okay. So you guys all know, guys, this is an ideal gas equation. Ideal gas law. Okay. So, dude, like. I tell you guys, this is the equation that you need to know for this chapter. Okay, I mean there's more equations you have to know, but this is one of them. The PVRT. So let's take a look at this chapter. Let's take a look at this equation, PVRT. So, so P stands for pressure. V stands for volume. Okay. T stands for temperature. It must be in Kelvin. Okay. And N stands for, guys, number of moles of gases, number of moles, number of particles. So that's basically, guys, what these, you know, like these guys are representing as a symbol. R is a constant. Okay, this is the constant. It's a number. So keep in mind, guys. So what's the purpose of a constant in a reaction, guys? So you got to ask yourself, what's the purpose of the constant in a reaction? So the purpose of the constant is. I'm not going to teach you math, guys, by the way. So constant is there to have an equal sign equation. So meaning, guys, pressure and volume, you multiply these two, they are proportional to N times T. Okay, they're proportional. Okay, so which means, guys, if you double the pressure, then like if you double this side will double too, right? That's what's gonna happen, right? But now, the values are not equal. They're not equal to each other, okay? So to make it equal, have an equal sign, they add a constant, okay? Which is what, guys? N times R times T, okay? So, which becomes equal to each other. So if you put like PV over RT, it becomes what, guys? Yeah, R. I'm sorry, NT, I'm sorry. It becomes R. R is a constant. So constant is a number, okay? And the value can change based on what the pressure is and what the temperature is given and stuff like that. But now, when the pressure we're using is ATM, so in chemistry, guys, we use ATM as a pressure, okay, or torr. They use these two a lot. Okay, if you're coming from bio, they use bar, like 1 bar, like 2 bar. But in chemistry, they use ATM and torr, or torr can be also, guys, millimeters of mercury. So. A lot of times, depending upon whether they use ATM as a pressure or torr or millimeters of mercury, guys, the value of the R will change. But if they use ATM, the value of R is equal to 0.0821. That's a value that you might want to memorize. Okay. So 0.0821, that's the value of R. Okay. When the pressure is being used as what? ATM. Okay. So the later stuff and the other stuff we'll discuss later. Okay. That's what the value of R is. It's a constant. So one of the stuff that I don't know if you take AP Bio or AP Bio, guys. There's an equation, guys. The soluble water potential. Okay, so which is equal to, guys, minus I times MRT. That's the equation for this. Same R. This is the same R value, but same R understanding MRT. But because the pressure for bio, they use bar as a pressure, they have a different R value here. Okay, like 0.0831, I think. So. Depending on the pressure, the value of R can change even though it's a constant, okay? So let's take a look at, guys, sorry. First thing first, guys, let's take a look at what ideal gas means, okay? What does it mean by ideal gas? That's one of the questions they get a lot, guys, as in terms of definition of an ideal gas. If you're coming from chem a little bit, guys, you should have an understanding of what they are, right? But ideal gas, to meet a requirement as an ideal gas, they have to, the requirements, right? Typically means they have to meet something we call KMT, okay? It's called kinetic molecular theory, okay? So KMT stands for what, guys? A kinetic molecular theory, okay? And to qualify for the ideal gas, this tells you what the qualification is, KMT, okay? KMT is what, guys? So in order to be an ideal gas, okay, first thing is what, guys? There shouldn't be any what? No IMF, intermolecular forces. IMF, we talked about it last week, right? IMF, intermolecular forces. So now, IMF is what, guys, again? It's LDF, London dispersion forces, hydrogen bonding. Okay, these are stuff, the dipole. Some of the stuff we talked about, okay? There is none of those, guys, okay? You cannot, as an ideal gas, there's no LDF, there's no hydrogen bonding, there's no dipole force attraction. Okay, there's none of those. No IMF. So you gotta ask yourself, right? If there's no IMF, okay, then what do you know about these particles? Which means like, okay, so there's no attraction between particles at all. There's no attraction between these two. Then what do you know, guys? So you gotta understand, guys, the attraction makes them what? So as a particles of a molecule, okay, the attraction makes them to what, guys? If there's strong attraction, what happens, guys? Hydrogen bonding, for example, what happens, guys? They become a liquid, okay? Or even what? They become a solid, right? They become a liquid or solid. But now, because there's no IMF, it doesn't matter how low the temperature is, how high the pressure is, they will never turn into what, guys? A liquid or solid, okay? So because what? Yeah, there's no IMF whatsoever. That is not true, okay? Keep that in mind, okay? That's not true, right? We can have a liquid hydrogen, very low temperature, right? But they're saying, okay, so no IMF, that's like, ideally, you cannot have a liquid or solid at all. But, you know, one condition, but I'm not gonna talk about it. Except for one condition. So that condition is what, guys? I mean, anyone know? When they reach what? A 0 Kelvin. 0 Kelvin is what they call absolute temperature, okay? Absolute zero, which is the lowest temperature you can possibly get. Everything is a perfect crystal at 0 entropy. Nothing moves, everything's solid. So except for a 0 Kelvin, they will never be a solid or a liquid. They're all gases. That's the first condition to be called ideal gas. You gotta memorize, by the way. So, you know, two guys, the other important thing to understand, guys. So this one is a little bit tricky to understand, so hopefully we can kind of hash it out today. I mean, if not, it's fine. But this one is a little tricky, and the AP really wants to understand this extreme, okay? The gas particles, the particles of gas, okay? So dude, like we have gas particles here, okay? The particles of gas have no volume, okay? So the gas particles have no volume. So which means, like, you gotta understand, like, so what this really means. So basically, guys, imagine this room is a container, okay? Like, let's say the door is closed, okay? Nothing goes out or in. And imagine, guys, like us, we are gas particles, okay? So think about it, guys. Can we have like 10,000 people in the room, guys? Can we have 10,000 people? 1,000 or more, like 10,000, guys? Can we have it in there? We can, because what? Physically, our volume will be greater than what? The room volume, okay? But now, if you're an ideal gas, okay, particles have no volume, which means what? Like, we have no volume, which means what? We can put what? Millions of us can be in the room because what? We don't have any volume. That's all the condition for the KMT, which means what? Yeah, like gases have no volume. They're just a type, so it doesn't make sense, right? They have mass, but no volume. You know what I'm saying, guys, here? So, which means, well, it doesn't make sense, okay? So, if you have a mass, you must have a volume, okay? Without the volume, you're like, dude, what the hell? It doesn't make sense. But according to KMT, gas particles have no volume, which means what? The volume of the container is the volume of the gas. If the volume is 1 liter, okay, the gas is in here. The gas volume is 1 liter, okay? The volume of the gas, the volume right here, V represents the volume of the gas, right? So the volume of the gas depends on what? Container volume. Container is 2 liters, the volume is 2 liters, okay? If the volume of the container is 3 liters, the volume of the gas is 3 liters. So that's what the KMT stands for, that's what they say, okay? Gas particles have what? No volume. Of course, that's not true. But just like the first one, okay, but these are the conditions you have to meet in order for you to qualify to use this equation. And third one, which you guys will not talk about too much. This one, I tell you guys, you might think it's really easy, guys, but this one is it's relatively difficult to understand, by the way. Like, equation perspective. 3 guys. So third one is so this one, they don't talk about it too much on your exam, I think. On AP Chem, they don't talk about it, guys. It means, guys, this means elastic collision. So elastic collision, I don't know if you guys have any background in physics, okay? Elastic collision means what, guys? So keep in mind, guys, here, gas particles, they will move around. Okay, gas particles, if you have a container, guys, if you have a gas in here, they constantly move around. So what happens is, guys, they will collide into the container, bounces back, that's what happens, right? They collide into the wall, bounces back. So when there's a elastic collision, okay, so when the things collide elastically, what happens, guys? What will happen is there is no loss of kinetic energy for the elastic collision. So which means, so in a simple way for you guys to understand this is what? If something hits a wall with a speed of like 2 meters per second, it will bounce back at the same speed. There's no loss of energy. Okay, so think about it, guys. When 2 things collide, they just bounce back at the same speed. And that's what they consider as elastic collision. So which means what? There's no loss of energy. So is this truly a true statement, guys? So when things collide, a lot of times they lose energy. Okay, like heat energy, guys, for example, like friction, for example, with collisions. But they're saying what? Okay, so gas particles, when they collide, there's absolutely no energy loss. That's to meet a condition for an ideal gas. There shouldn't be any what? Energy loss based on collision between the gas particles or the particle to the wall. Okay, it's simple, right? It's not too bad, right? But I don't know why, guys, they don't talk about this too much. Okay, AP guys, this is not something they talk about, guys, a lot. Because probably they think elastic collision is a term they use in physics, and I don't know, they don't care if you took physics or not, but they don't talk about it too much. And fourth one, this, guys, is very, very important, by the way. Fourth one, guys, absolutely, guys, you have to understand the equation today. The fourth one, I'm going to write here, right? Fourth one is the average kinetic energy of the particles, okay, is equal to 3/2 times RT. That's an equation that you have to know. Very, very, very important equation for Chem, okay? Keep in mind, guys, this R right here, same R as this R. Same R value, it's the exact same R value, okay? But, same constant, it has a different value though, okay? So, this equation tells you what, guys? If temperature, so this is a constant, right, is proportional to average kinetic energy of the particles, gas particles, okay? Which means if temperature goes up by twice, for example, guys, like 200 Kelvin to 400 Kelvin, if temperature doubled, okay, kinetic energy of the particles will double, okay? That's what this equation means. They'll move at a faster speed. That's what this equation represents. So, keep in mind, guys, by the way, this does not apply for gases only, okay? This will apply for what, guys? Solids and liquids as well. Okay, this is a universal equation. It doesn't only happen in the Earth, it happens everywhere else. Same equation applies as a universal. Okay, so this, this, and this, they must qualify with these terms for the particles to what? Be able to use the equation. Okay, so in order to use the equation, guys, they have to qualify the KMT. Okay. So, more to come on this one, by the way. So, I don't know. So, keep in mind, guys, let's talk about this one a little bit more, guys, okay? Kinetic energy. So, the two things you probably heard a lot, guys, is the potential energy and kinetic energy, right? So, the kinetic energy, by the way, so keep in mind, potential is what? It's something that is hard to define. The potential is something you can't really explain too much, okay? So as we discussed, guys, potential energy is what? It's something that you need a benchmark. Put your phone away, please. Okay, so if I break the phone. So potential energy is what, guys? Is basically, so it's how much energy is stored like within a substance. Okay, and now potential energies, guys. Okay. Again, like it's like I told you guys, it's like measuring a smartness. Okay, like okay, so how smart are you? Like how much potential do you have? You know, you gotta have a benchmark. Okay, like a standard point. Okay, a lot of times, guys, standard point is what, guys? Like 0 joules is the potential for standard for potential energy. Okay? I'm not gonna repeat this again, but kinetic energy is relatively simple. Okay, kinetic energy, guys. You have to know the equation for this, by the way, for the AP. Kinetic energy of the particle depends on the speed and the mass of the object, okay? 1/2 times mass of a substance, okay, of a particle, times what? Their speed squared. That's the equation for a kinetic energy, okay? Which means, guys, anything that has a mass and a speed will have kinetic energy, okay? So, like, if you got a mass and speed, you have kinetic energy. Okay, so look at this equation, guys. Okay, if temperature goes up, kinetic energy goes up. All right. So okay, so kinetic energy goes up. What happens, guys? If this goes up, what happens, guys? If the mass is not going to go up, right? Like they just don't get mass, right? Speed goes up. Okay, so dude, I'm not here to teach you math here. Okay, so if you think about it, right? If temperature doubled. Okay, so again, like ask your math teacher, guys. I mean, I'm not doing this, guys. If temperature doubled, but this can be on the AP, they'll ask you, okay, what will happen to the average speed of the particles? It goes up by what? Square root 2. Okay, so again, like you couldn't ask me like why is square root 2? That's not my question, guys. Ask your math teacher. Okay, so which means again, the equation is it's what 3/2 times RT, okay, is equal to this equation right now. Okay, so temperature is proportional to speed squared. Okay, if I double this, speed should go up by what, guys? Square root 2. There's a square sign here. That's a question for math. Okay, so hopefully math is all there, guys. Just so you know. So again, if the speed doubled, then temperature should have went up by what? 4 times. So you know, what? There's a square there. There's something else here. So that's one of the things to understand, guys. Here, okay, with the equation. So these are the conditions, guys, with KMT that needs to be met in order for it to be called ideal gas. So you know, and I'm not kidding, you gotta know all of it, okay? Except for this one. This one, not too much. So let's take a look at, guys, the ideal gas equation. So let me tell you something, okay? So this equation, ideal gas law, okay? This is something that so they have a, if you read the chapter, guys, I mean, they have an individual reaction, individual equation, okay? Like Boyle's law, Charles' law, Avogadro's law, you know, like Gay-Lussac, whatever, okay? So like Boyle's law, they discuss the P and V, pressure and volume relationship, okay? And then the Charles law, they look at volume and temperature ratio and stuff like that. So everything combined turns into ideal gas law, okay? So everything combined turns into this equation. So do you not have to know this, like Boyle's and Charles and Avogadro, Gay-Lussac? I mean, do you have to, like, can you ignore this? Personally speaking, guys, for AP, yes, you can ignore this, okay? Like Gay-Lussac, I mean, maybe your teacher maybe wants you to know them, I'm not sure, guys. But is my recommendation is to know them? Yes, I do, okay? Because I'm not kidding, guys, okay? I'm not like making this up, guys, okay? I'm sure a lot of you guys are like pre-med, right? But dude, I'm not making this up, guys. I mean, the MCAT exam. Yeah, so I tell you guys, the level of the MCAT is not too different from AP Chem. It's very similar, guys, just so you know. So MCAT has something called PS section. PS is physical science, which has chemistry in it. Okay. So I took the one back in 2006. Okay. I used to teach MCAT too. So one thing to note. They have a question, dude, I'm not kidding. Dude, I'm not kidding, guys. They have a question on, this is not on my test, on my friend's test, we took the same day. They asked a question on, okay, Yeah, which of the variables are considered in Charles law? I mean, it's a very, very elementary stuff they ask. Okay, oh yeah, by the way, based on choice A, B, C, D, okay, which is the equation for Charles law? Dude, I'm not kidding. That was on my friend's exam. Okay, so which is Charles law is this. So keep in mind, guys, MCAT. I don't know about now because I haven't taken a look at these questions like for a long time. Okay, I used to teach back in 2010. I started teaching. I'm not sure when, but so one thing to note, guys. Yeah, AP, right? Like, dude, AP, one question wrong, still 5. Okay, 2 questions wrong, still 5. 3 questions wrong, still 5, right? MCAT, no. 1 question wrong, guys, score goes down. Just so you know. So it's a big deal, guys, to not anything get wrong. So my recommendation is, guys, be thorough, know them all. That's my recommendation. But for AP, like, you guys are AP, so if this is recorded, guys. I mean, I'm not making this up. Okay, so the first thing my friend asked me when he came out of the exam for the lunchtime was like, "Oh, dude, what's Charles law?" That's the first thing he asked me. So, so my recommendation is, guys, know it all, but we don't have to talk about it because like AP, like who knows? You know, they might not. You don't have to know it, but you guys have to do your due diligence, guys. Okay, for whatever that's coming towards your way. So this is the only thing to talk about. I'm not going to bring up the other equations, which is probably part of the reading. I'm not going to talk about it, guys. Whatever. So let's talk about individual variables here, guys. And let's see. Okay. So pressure. So pressure. So guys, a pressure. Let's understand how a pressure can be exerted. Okay, like how can pressure be exerted? Okay, by gas particles. Okay, pressure by an equation. If you take physics, it's force divided by surface area. That's what pressure actually is. Okay, by definition, you have to know that. I mean, I don't know. The teacher might talk about it. I'm not sure. Whatever. I don't care. So, how can a gas particle exert pressure? Okay, how does it work? So, pressure exerted by the gas particle is what, guys? Pressure is basically, okay, you have a container, okay, and the gas particles, they move around. So at a certain temperature, as you know, they have some kind of speed. They move, okay? At a certain speed, they move around. What happens, guys? As they move, what happens? They bounce off of the wall. They exert some pressure on the wall. This is right there. The force gets exerted on the wall by what? Them colliding onto the container. Okay, that's where the force is at. Force is coming from what, guys? A particles colliding onto the wall by the gas particles, right? Like gas particles collide with the wall, and they exert force and bounces back. That's where the force is for the gas particles, okay? And what? The surface area of the container. And that's how the pressure of the gas is being exerted as a collision perspective. So then, okay, so that's how the pressure is, guys, and the pressure is measured with a unit of what? I said it ATM, or what? Torr. So 1 ATM, okay, by the way, is equal to 760 torr. Okay, they're proportional. Okay, 1 ATM, 760 torr. Sometimes, guys, they use a 760 millimeters of mercury. So torr, the unit torr, guys, is derived off from what? Millimeters of mercury. Okay, they're the same thing. Okay. And now, keep in mind, guys, 1 ATM is equal to 101.3 kilopascal. Pascal is the SI unit for pressure, okay? So 101.3 kilopascal is equal to 1 ATM, which can be equal to 76 torr. They're all the same thing. Okay, so the pressure is same, the value is not the same, but the pressure is same with the different units here, okay? So, kind of give understanding, guys, of the comparison. 100 kilopascal equals 1 bar. That's the conversion for bar to a kilopascal. So, if you're coming from a bio, guys, 1 bar is very similar to the ATM pressure value, okay? But that's conversion, guys. I mean, so sometimes they give you ATM in chem, torr, but never in the AP as a kilopascal. They never use kilopascal in chemistry, I'm sorry, or even bar. They don't use this. So in chem, guys, only time that you'll get these kilopascal or bar is when you guys take Olympia chemistry. They have a kilopascal there, they have a bar there as a pressure value as well. But for AP, I'm sure, I don't know, your school teacher, by the way, they probably use this one and this one at your time, okay? So that's a unit, guys, by the way. And then keep in mind, guys, based on the unit of pressure, okay, that can change, the value of R. We talked about it, right? And can you, so first thing first, guys, can you have a negative pressure, guys? What do you think? Can you have negative pressure, guys? No, you cannot have negative pressure. It's always, well, pressure value is always positive. Keep that in mind. Let's think about volume, guys. Because volume, guys, we talked about it. A lot of times volume is given as liters. Liter is a unit for volume. Okay, so as we discussed, so guys, the container volume for the ideal gas, the container volume is what, guys? Volume of the gas. It doesn't matter how much gas you have in there, guys. Container volume is the volume of the gas. Okay, very simple, nothing fancy. Okay, and volume should be in liters. Okay, if you're gonna use the equation, guys, the volume must be in liters. Okay, make sure I'm saying, guys. And now, if you take a look at this, guys, N, as we discussed, the number of moles gases, right? Number of moles of gases, okay? So N represents, guys, number of moles of gas. So, which is how much gas particles you have, right? 1 mole, 2 mole, 3 moles, whatever. So you can kind of think about this, right? How do you increase pressure? How can the pressure increase? Like, how do you increase the pressure? So if you think about it, guys, I mean, so yeah, if you have a container with some gas particles in there, you have to ask yourself, guys, okay, so what do I do to increase the pressure? Pressure is what, guys, again? Pressure is what? Force over area, which is how much of a force exerted by this container by the gas particles, right? That's what we call the pressure. So how do I increase the pressure? That's something you have to ask yourself. So, which is what, guys? I mean, what I can do is what? I can add more gas particles. I can add more gases. Okay, if I add more gas, what happens, guys? There's what? Greater frequency of the collisions. Okay, there's more collisions per second, right? So instead of having like 5 collisions per second, I can have 10 if I have more particles in there. So which means what? If I add more gases, the pressure should increase. Okay, no question there, because what? The frequency of the collision should go up. Okay, because that, if you look at the equation, guys, it aligns nicely if you think about it, right? If the number of moles goes up, number of gas particles goes up, what happens, guys? Pressure goes up. Okay. And also, what can you do, guys? You can increase the temperature, right? Like, you can see how this goes up, goes in, guys. If temperature goes up, so this is where you gotta have a good understanding, guys. Temperature goes up, what happens, guys? Temperature goes up, kinetic energy goes up, they move faster. Okay? If they move faster, what happens, guys? They will collide with greater force. If the force goes up, so they collide with greater speed, the pressure goes up. Okay? So now, yeah, look at the equation, guys. Temperature goes up, what happens, guys? Pressure goes up. Okay? That's the understanding, right? So this equation tells you guys, okay, so it's sort of, if you look at it, guys, kind of tied to each other in a certain way. Okay? That's the other gas equation, okay? So what do you have to do with this equation? Because you know the equation, you're given the equation, guys. So what do you have to do with the equation? They will give you a question based on this. You have to be able to solve questions using the equation. So such as what? So, and if you have a little background in chem, guys, then you probably have seen the equation and use the equation to get an answer somehow, somewhere down the road. So let's take a look. Very, very simple, but at the same time, like I think some kids, some students, this is not where they will struggle. Okay, with this PVNRT equation, by the way. So kind of an example, right? Something that you'll see in the homework, whatever, you know, on the AP, is they give you information about the gas in the container itself. Okay. So for example, guys, this is like a 2-liter container. Okay, and the pressure of the container is 600 torr. Okay, and temperature is equal to 300 Kelvin. Okay, so you have a 2-liter container, you have a gas in here, 600 torr as a pressure, okay, about 300 Kelvin. And they'll ask you, okay, so they are going to reduce the volume, okay, into 1 liter. The volume went from 2 to 1 liter, okay? And then the temperature has gone up to 600 Kelvin. They can ask you guys, okay, what is the pressure? What's the new pressure? So the volume has gone down to 2 to 1. Temperature has gone up from 300 to 600 Kelvin. They're going to ask you, okay, what the hell happened to the pressure of the gas? That's a question, a very simple question you've probably seen before. Okay? So then, again, you can utilize whatever method you know. I mean, if you already know how to do this question, guys, I mean, whatever method you utilize, I mean, that's fine, okay? So I don't care, guys. So for repetitions, you can use PV&RT equation to kind of figure this out, okay? So keep in mind, guys, unless otherwise mentioned, okay, other than pressure, volume, and temperature, because I didn't say anything about number of moles gases, right? But there are four variables here: pressure, volume, number of moles, and temperature. Okay, so seems like what pressure, volume, and temperature is changing, and there's nothing said about number of moles here, which means what? This is not changing. Number of moles right now seems to be not changing, unless they say, oh, we added more gases, and it's not changing. That's a given. Okay, R is a constant. So these two values are not changing. So what do you have to do? So pressure changes, volume changes, temperature changes, right? What do you do, guys? So you might want to modify the equation, okay? Put changing variables into one side of the equation, okay? So what do you do, guys? Divide by t on both sides. What happens, guys? Yeah, basically what the equation becomes PV over T equals N times R, okay? So think about it, guys, right? So you can change the pressure, volume, and temperature all you want with this gas. But when you do PV over T, when you multiply the new pressure and volume over new temperature, they still have to equal to what, guys? N times R. You know what I'm saying, guys, here? So which means what? The equation becomes P2 D2 over what? T2. That's the equation. You know what I'm saying, guys? So this equation right here, guys, PV over T with PV over T, guys, that's what they call combined gas law. Okay, but do you have to know that, guys? You don't, because why? You can just derive it from PV&RT equation. That's not needed, guys. So what do you do, guys? Plug in numbers. Okay. So which is looking at the 600 Kelvin, 600 torr, I'm sorry. The volume is 2 liters divided by 200 Kelvin is equal to. So let's take a look, guys. Okay. Pressure P2 is what should calculate. The volume is 1 liter divided by 600 Kelvin. So that's the equation right now that I set up. And all you have to do is what? Yeah, I'm like, okay, so try to figure out an answer. Okay, so cross multiply. So you can reduce this by 2 first. Okay, and then if you look at it, guys, it's 4. So this is like 4. This entire thing becomes 4 here. So 4 is equal to P2 divided by 600. Okay, so what's the new pressure, guys? 2,400 torr. Okay, so P2 is what, guys? 2,400 torr. That's the answer. So like it's a very simple way, okay? That's one of the easy questions that we given down to you, okay? So yeah, what's the new pressure, guys? 2,400 torr, based on what we just talked about. Did I do it right? Minus? I think so. Oops, sorry. Question, guys. So something in the line of this is where you have to do your work. Okay, utilize the PV&RT equation. Okay? So that's something that you'll be asked to do. Which is like that's not that hard at all, right? Any questions? Let me know, guys. Questions, let me know. With PV&RT equation. So I'm not going to go too crazy with the PV&RT, guys, but there's a lot more to talk about than PV&RT equation. Sorry. All right. So let's take a look at, guys, other stuff that you guys might have to know for the EP. So among other things, guys, that really cost my mind, guys, right now is the equation for equation for partial pressure of the gases. Okay, so there's another portion you have to know: partial pressure. This seems to be very simple conceptually, okay? But a lot of students really struggle with this question, by the way. So, like, okay, let me tell you guys, the problem with this sector of gas chapter is they understand what this is, okay, partial pressure is, okay? But they don't know when to apply this, okay, on a question. That's where the problem comes in. So let's talk about what this is, partial pressure is, okay? So partial pressure, guys, okay, is something like this, okay? So your container, okay? And now so you have guys, for example, N2 gases and O2 gases, ideal gas, okay? N2 gas and O2 gas. And let's say, for example, guys, okay, so total pressure total is equal to 1,000 torr. 1,000 torr, okay? Total pressure right now. So let's do something simple here, okay? So the pressure due to N2 gas is equal to, right now, 600 torr. Okay? So right here, so total pressure is 1,000. The 1,000 pressure torr is exerted by two gases. Two gases exert on the wall, blah, 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 you know, they will exert, so N2 gas will exert 600 torr, okay? That's the pressure exerted by the N2 gases. That is what they call partial pressure of N2 gases right now. Then, yeah, dude, like, what do you think the pressure of the O2 gas is? I mean, like, dude, okay, that's basically what it is. That guy, 600, what do you think, guys? This is what? Must be 400 torr. Do you understand, guys? And that's what partial pressure is, okay? Which is 600 torr, 400 torr. The equation is what, guys? Okay, so pressure of the N2 plus pressure of the O2 becomes equal to pressure of the total. It's a very simple understanding, right? So the partial pressure understanding is what, guys? Different gas particles exert pressure independent from each other. So this gas exerts pressure on their own, and that gas exerts pressure on their own, okay? Independently exerting pressure by themselves. That's the definition of what? The partial pressure of the gases, okay? So for example, guys, think about it, guys. In the atmosphere right now, you have N2 gas and O2 gas and like some other gas, CO2 gas, whatever, okay? They exert pressure independent from one another, okay? That's what we call partial pressure of the gases. So now, if you look at this, right? So again, it's very simple, nothing fancy. You know, oh my God, how can this be so easy? So, but this gets a little bit complicated now, okay? So let's assume right now, guys, just in the formula we know, we have, think about it, guys. We have 4 moles of O2 gas, okay? And then we have 6 moles of N2 gases right now, okay? So there's a different equation for the partial pressure, which is the partial pressure of the N2 gas is equal to mole fraction, okay, of N2 gas times pressure of the total. That's also an equation, guys, you have to know, okay? So this is so that, aside from this equation, guys, which is like, yeah, if you add a total partial pressure for all the gases, it adds up to total pressure. But now if you want to calculate a particular partial pressure of a certain gas, it's the equation, guys, okay? Which is like, kind of make you understand, guys, 600 torr, which is what we have for the pressure of the N2 gases, is equal to mole fraction. So mole fraction is what, guys? Number of moles of N2 gas divided by the total number of moles gases. So to how many moles of N2 gas overall? So 6 divided by 10. So there are 6 moles of N2 gases. Total is what, guys? 10 moles. 6 plus 4, right? Times what? 1,000. Pressure total, 1,000. So that is only the equation, guys, for the partial pressure of the gases, calculation perspective. So, which means what? Yeah, the pressure, there's no question there for the PDNRT, number of moles and pressure are proportional, okay? But it's very simple, yeah, whatever, man. Like, this is where the problem comes in for the students, okay? This is the question, guys. If I added, so we have a 6 moles and 4 moles of all the gases, right? If I added 6 additional moles of N2 gases, okay? So we have 6 and 4. I added 6 more of N2 gases. I have 12 moles of N2, 4 moles of O2 gases, okay? The question becomes, okay, then what will be right now the pressure of the O2 gas? What's the partial pressure of the O2 gas now? What do you think, guys? So, okay, so I added more N2 gases, right? Yeah, what do you think? Who has the answer, guys? Let me know. Like, figure it out. I'm going to give you 1 minute. 1 minute, guys. I added more moles of N2 gases. Okay. So now my question is, what's the partial pressure of the O2 gas? 1 minute. That's all you need. You need like less than a minute, actually. Anyone have the answer, guys? Let me know. So just to give you a little hint, guys, there's no calculation needed for this. Okay? Anyone have the answer, guys? What's the partial pressure of N2 gas? Anyone know? After I added 6 moles of N2 gas, what do you think? The answer is 400. Why is 400, guys? Why? Remember what I said, guys? What is the partial pressure again? So if you're trying to calculate something, guys, I mean, so yeah, think about it, guys. What's the partial pressure? Definition was what? I mean, not definition, but like understanding is what? The gases exert pressure independent from each other. Okay? So O2 gas exerts pressure on its own, N2 gas exerts pressure on its own. You know what I'm saying, guys? So think about it, guys. I add more N2 gases. Okay? Does that change anything for the O2 gases? Does it change anything, guys? Does it change anything for the O2 gas? So think about it, guys. Look at PBRT equation. So to change the pressure of the O2 gas, right? You want to change the pressure of the O2 gas, right? What do you have to do? Which means, did the volume change? Yeah, did the volume change, guys? Container volume, did it change? No. The number of moles of O2 gas change? Did I add more O2 gases? It's still 4 moles, right? Yeah, did temperature change, guys? No. Yeah, why would the pressure change? Because why? Dude, they exert pressure based on understandings, well, independent from each other. Which means what? Dude, I didn't do anything for the O2 gas, which means what? The pressure should not change at all. You know what I'm saying here? So that's the understanding of pressure of the gases. Okay? So it's like, I don't know, like you gotta treat them separately for the partial pressure understanding. Okay? So yeah, 400, I didn't change a single thing about this. Okay? What's gonna change? What's gonna change? If I had 6 moles of N2 gas, what happens, guys? I mean, like, yeah, partial pressure of N2 gas will change. Okay? Like, okay, so they have 6 moles of N2 gases. Okay? Now add what? Additional 6 moles. So based on the PBRT equation, if you look at this, what happens? Or you can take a look at this if you want to. But now, just based on the equation for the PBRT, if you double the number of moles of gases, what happens, guys? The pressure doubles. Okay? Which means what, guys? Pressure of the N2 gas initially was what? 600. Okay, now added what? Same N2, 6 moles of N2 gas, which means what? The pressure now should be 1,024. Because what? The pressure doubled because what? Number of moles of N2 gas now is what? Is 12, which is what? Double the number of moles of gases. That is the understanding for what, guys? Partial pressure of the gases. Which is like, dude, is it hard, guys? I mean, like, okay, so the concept is really easy, okay? But students really struggle with understanding when to apply the logic of partial pressure for the gases, okay? Any questions, guys? So there's more to discuss. Questions, guys? So what kind of questions, like students really struggle with this, partial pressure understanding, is this. So this is like you know, just an example, okay? Questions you'd be getting, guys, is stuff like this. And I tell you guys, let me tell you guys, okay? It doesn't matter how much time I spend time to explain this, they still get it wrong, okay? So, you know, so I don't know. So AP have questions like this. I'm not making this up, okay? They have containers. Container A, B, C, okay? So basically, guys, this is 1 liter container, 1 liter container. I'm gonna make it easy for you guys, okay? 1 liter container, 1, 1, 1. And now, what will happen is, guys, here, basically what will happen is here, so I have N2 gas here, I have O2 gas here, I have H2 gas, okay? I mean, I'm not H2, I'll use a helium gas, just in case there's a reaction between H2 and O2 gas, kind of banning from that, guys, so I have 3 gases here, N2, O2, H2, okay? Pressure of the N2 gas is 5 atm. Pressure of the O2 gas is 2 atm. Pressure of the helium gas is equal to 10 atm. Okay? So 5, 2, and 10 atm for nitrogen, oxygen, and helium. Okay? Temperature is all the same. Temperature stays at 25 degrees Celsius. room temperature. Okay? Okay, keep in mind. Okay, so keep in mind, room temperature is not 25. It could be room temperature is there's no set temperature value for room temperature. Okay, room temperature could be like whatever temperature the room is. Sometimes it's cold, sometimes it's hotter. You know, room temperature, but approximately 25. Okay. So now I'm going to put all the gases together. Okay, into 2-liter container. So I'm going to take this gas, N2 gas out, put it here. Okay, take this guy out, put it here. Take the H2 gas, HE gas out, put it here. The question on the AP is, what is the pressure total? That's the question. What is the total pressure? I'm going to give you guys a couple minutes, guys, to solve this. Okay, take these gases out, put it all together in one container. Okay, take every one of these out, guys. You mix them. Okay, so now you have an N2 gas, you have an O2 gas, you have a helium gas. Okay, so if you add the pressure for all, what's the total pressure? Okay, that is a question of the AP. Okay, in regards to a partial pressure understanding. Okay, so I'm going to give you guys right now 11:52. I'm going to give you up to 11:55. That's it. Okay. Temperatures stay the same throughout the whole thing. I already have the answer, guys. Okay? I just made up the question, guys. I know what the answer is. No calculator needed, guys. Calculator probably is not needed, guys, for this. Okay. Anyone have the answer, guys? Anyone got the answer for this? Anyone? Anyone? Confident enough to tell me the answer, guys? Let me know. No one? No? All right, so let's take a look at it. Yeah. So this is how the question is designed. Okay. Multiple choice. I'm telling you guys, they give this question the multiple choice on the AP Chem. Multiple choice. It's the calculator not required. Calculator not allowed, not required. So not required. No, it's not allowed. So you can't you can't I don't know, try to use equations for this. I mean, you have to, but it's the conceptual question you have to understand. Okay, like how I'm gonna approach the question. So yeah, as I mentioned, okay, partial pressure is what? They exert pressure. So you now have what? N2 gas, O2 gas, and helium gas, right? They exert pressure independent from each other. Do you understand what I'm saying? So so for N2 gas, it doesn't matter if the other two gases are there or not. It doesn't matter. Okay. So now, yeah, look at this. Imagine an O2 gas and helium gas is not present. Dude, imagine these are not there. Okay. You're only looking at N2 gases only. N2 gas, you're putting into a big container. So the volume is 1 liter, but you're putting into what, guys? A 2-liter container for the N2 gases. Okay. So now, what you do is this. You take a look at PVRT equation. So that means right here. So PVRT. So yeah, what is changing? So if I take all the N2 gases, just throw it into a bigger container, the 2-liter container, from 1 liter to 2 liters, right? What is changing? So it seems like number of moles of N2 gas is not changing. Because what? If I had 1 mole, that stays the same. Okay? R is a constant, temperature is not changing. So these are not changing at all. nRT is not changing. Number of moles, constant R, temperature is not changing. What's changing, guys? Pressure and volume is changing. Okay, so which means what, guys? I'm going to start the equation. This is equal to what, guys? P2 times V2. It's the equation. So initially for the N2 gas, the pressure is 5 atm, volume is 1 liter. Okay, which is equal to whatever this is. P2 is what, guys? P2, I don't know. I'm trying to find it out. Okay, volume is what? 2 liters. So what's the P2 then? So 5 equal to what? P2 times 2, which is what? P2 will be 2.5 atm. You know what I'm saying, guys? It'll be half of the pressure. So pressure of N2 gas here is what, guys? Okay, it'll be what, 2.5 atm is the pressure of N2 gases. Okay, that's the partial pressure of N2 gases only. You understand what I'm saying? Yeah, so okay. What about, so like I don't have to do all this, right? What about if I put O2 gas over there? What will be the pressure, guys? 2 to what? Do the same thing. If you want to do it, guys, what happens, guys? That becomes a 2 here. What happens, guys? It becomes what? 1 atm. Okay, the partial pressure of O2 is what, guys? The pressure of the O2 gas is 1 atm. Do you understand, guys? Because it'd be half of the pressure. So that's 2, the volume doubles, the pressure halves. Pressure of the helium gas is what, guys? Okay, so it'll be, here is 10, which means what's 5. So overall, what happens, guys? Becomes what, guys? 8.5. You add 5 plus 1 plus 2.5 is what, guys? This becomes 8.5 atm. That's the total pressure. And you are solving it how? Understanding of what? Partial pressure of the gases. Okay? You look at them individually. Okay? It becomes a lot simpler. Okay? When you look at it individually. This is AP. This is, guys, what they expect you to know for the AP questions. Okay? Multiple choice. Like that's how you solve it. Is there a different way? Yes. You can use equations and all. Try to get the pressure. Blah blah blah. But no, this is how they want you to understand the question and solve the question based on this. Okay? Any questions there, guys? Question wants to know. Questions? If you don't get it, guys, like, oh my god, like, you gotta let me know, guys. Okay? If you don't get it, guys, let me know. I'm not making you like you don't have to be a like expert at the gases today, but it's good to know what else is happening. Okay? Any questions there? No questions? Okay. So, I mean, that's a high level, guys. What you guys have to know for the partial pressure of the gases. Okay. So, so now, guys, let's take a look at. Among other stuff that you have to know, they will talk about density of the gases as well. Okay, density of the gases. Density of a gas. Okay, so density. What's density, guys? Density is what, guys? Mass of the gas over what? Mass over volume, right? They'll talk about the density of an ideal gas. Dude, I am not kidding. You have to know the equation of density. Okay, like I mean, not mass or volume. Like this is like second grader stuff. Okay, ideal gas density. Okay, like they'll ask the question. So if you look at it, guys, how do you get it? Like, oh yeah, by the way, oh yeah, the pressure is like 1 atm, temperature is whatever, like volume is whatever. Like how do you get the density of an ideal gas? Okay, or they give you 2 different gases which are the higher density. How do you get it? So. Like, yeah, believe it or not, I mean, I'm not actually memorizing the equation today, but like few days before the AP or maybe your school exam, I'm not sure, man, you gotta memorize the equation for density, okay? And my recommendation is, so this is my recommendation, okay? Some kids follow, some kids don't, okay? You might wanna learn from me how to derive an equation, it's nothing fancy, okay? To get a density of the equation for the ideal gases. So every equation derives from PV/RT. Pressure times volume equal to N times RT. This is where we can try to get a density of a gas equation. Okay, nothing fancy, dude. Like it's very simple. Density is what, guys? Mass over volume. I have a volume. I have a volume of the gas. Okay, all I need is what, guys? I need to have a mass of the gas. That's all I need. So, but we don't have a mass in the equation. Okay, so we have to create a mass in the equation. I need the mass in the equation, right? But now, mass is somewhat incorporated into what? The number of moles. Okay? So now, like, imagine, guys, right? Yeah, so number of moles is what, guys? I have 1 mole of carbon. Okay? What is that equal to, guys? This is equal to what, guys? It's equal to what? 12 grams of carbon. Okay? That is the mass, right? So now, so now, yeah, what if I have 24 grams of carbon? How many moles do I have? I have what? 2 moles of carbon. So what's the conversion, guys? So which means what, guys? Mole is what, guys? Mole is equal to what? Mass over what? The molar mass. Okay, molar mass is what, guys? 12 grams. What 1 mole is equal to. Okay, so which means what? Okay, so mole of a gas and mole is equal to what, guys? Of a substance is equal to what, guys? Mass of a substance divided by what? It's molar mass. Mass over the molar mass becomes 1 mole. Okay, becomes their mole. So now, if you look at this, right? So I can convert this. So N is equal to mass divided by its molar mass. Just like what, guys? Oh yeah, like if I have 24 grams of carbon divided by their molar mass, I got what? Okay, I got 2 moles of this carbon, like carbon molecule, right? Carbon atom, sorry. So then I'm going to convert this equation, guys, okay? Into pressure times volume is equal to what, guys? Mass of a gas divided by its molar mass times RT. That's the equation right here. So now I have the mass and volume of the equation, okay? So dude, like, I tell you, like, this is something you might want to memorize, okay? Like how to derive, okay? Not like if you can't memorize it, guys, dude, I tell you guys, I'm teaching like a lot of stuff, right? Like bio, chem, and like physics. I'm teaching a lot. Only time that I can memorize the equations is what? Some of the equations, guys, I know how to derive them. If I forget, I mean, dude, I just derive it, okay? So if someone tells me write the equation for the density of a gas, I can't do it. I can derive it, but I can't. It's not in my head. So how do I get mass or volume? So I have a mass here, I have a volume there. Okay, this becomes a simple math now. Okay, cross multiply, you know. So here's what, guys? Pressure. So again, like the cross multiplication, guys, it's what you have to do. Okay. Pressure times, I can switch these over around. So pressure times molar mass of the gas divided by RT is equal to mass over volume, which is equal to density. That is the equation, guys, for density of ideal gas. Right there. That's the density equation for a gas, for ideal gas. Okay, pressure of the gas times the molar mass divided by the RT. R is a constant, RT is what, guys? Temperature. So keep in mind, guys, they will be asking you, okay? So they're gonna give you a bunch of gases at different conditions. They're gonna ask you guys, okay, by the way, you know, which of the following gas have a greater density? Okay, so yeah, it's the same temperature. So you gotta look at what? Pressure times the molar mass of the gas, and you'll be able to what? Figure out the density of the gas, which is highest density, lower density, for example. So the one that has what? Greater pressure and greater molar mass, you know, and the lower temperature should have what? Higher density. This is a question they used to also have in SAT Chem. Of course, the AP guys, they have to know a little bit more for this question, by the way, okay? Like for the AP guys, you have to really know the equation to understand density of the gas, for example, okay? So know the equation, guys, like the time, guys, I can't like figure out a question every time, guys, we have this, by the way. But there will be a question on this chapter where you have to look at they're going to be different gas examples. They're going to give you the pressure, and then they'll figure out, okay, so which one of the following has the highest density? So that's one of the stuff you have to know the equation for. Okay? Any questions, anyways? Nothing fancy. Okay? Like if you know the equation, you get it right. If not, guys, the question will be very difficult for you guys. Okay, so now before I move on to, guys, like other stuff, like I'm sure when you guys do, I look at the Colmar question, guys, yesterday. And they had some vapor pressure stuff in there, and like IMF and vapor pressure, some gas stuff in it. So that's the reason why, you know, I thought it was a little unfair to give those questions actually for the homework. But before I go there with the phases and all, okay, I do want to talk about one more thing about the gases. It's at a high level right now, guys, by the way, which means like there's a lot more to talk about because I'm just skimming through right now. So this is a big deal, okay? This is the sort of the hardest part of this entire, the gases, which has to do with deviations. Deviation of an ideal gas. So I will not go too crazy with this right now. Deviation of not ideal, real gas. The deviation of the real gas for the ideal gas. Okay. So again, like, dude, we don't have ideal gas. We got real gases, right? So the question becomes, guys, okay, so how do they deviate? Okay, and also, so one of the few things that you should already know is what? How does a real gas deviate from the ideal gas compared to ideal gas? And how can you make a real gas act more ideally? Stuff like that, right? So let's take a look at, guys, the real gases and their deviations. Okay. Easy ones first, okay? Easy ones first, okay? So now, real gases, yeah, what do they have? Like, what do they have? They got IMF. Dude, there is attraction for the real gases, right? Like, dude, they got IMF, right? They got what? They got volume too, right? They got volume too as well. Okay, so, I mean, like, okay, so based on the KMT, they should not have IMF, okay, and they should not have any volume at all whatsoever, right? So, so like, okay, so the AP question, even AP questions will ask you, okay, so which of the following is the best condition for the gas to act ideally? So because they have IMF, what's IMF, guys? The particles what? Start to attract each other, okay? They will attract. So how do you make IMF relatively negligible? So how do you make it like go away? So what can you do to make the IMF like, just not there? Or to minimize or make them negligible is a question to ask yourself. So one of the ways what, guys? One of the way is increase temperature. Have a high temperature for the gases. Make the temperature high. So how does that help, guys? If you have a high temperature, what happens, guys? Temperature high, it means what? It has a greater average kinetic energy. Okay, just like how we talked about, right? The equation, right? So temperature high, higher kinetic energy. Yeah, what does it mean, guys? What does it mean, guys? There's what? There's a higher speed. Let's see what it means, guys. Okay, so they move at a fast speed. What happens, guys? Yo, what the hell happens, guys? They move fast. So keep in mind, guys. Imagine, like, think about, guys, when water turns into a liquid. Yeah, when does water turn into liquid? When what? Temperature is what? Below 100 degrees Celsius. So if temperature is above 100, what happens, guys? They will never be what? They'll never be a liquid. I mean, temperature, pressure stay the same, right? So because what? They move too fast. Okay. Hydrogen bond is what? Too weak to make them what? Settle down. So if temperature is high, the particles move too fast, okay, which makes what? Which makes the IMF negligible, okay? They have to move at a slow speed to what? Lock up and what? Turns into a liquid or solid, okay? That's the reason why, okay, it deviates less. For the real gas, at a high temperature, is what? If they go fast, which what? Makes the IMF relatively negligible, okay? For the like low-level classes that I used to teach, so imagine, guys, okay? You have two cars, you tie them with a very thin rope, okay? If the cars move at a fast speed, what happens, guys? Yeah, the rope will be cut, okay? But the cars move slow, what happens, guys? The rope will not be cut, they'll be hanging together, right? So that's the same understanding, okay? So if they move at a fast speed, what happens, guys? IMF will be relatively negligible, which means the real gas will act more ideally, okay? What the volume? Volume, what do you think, guys? So this is a tricky one. Oh yeah, this one, guys, it's a hard one because the real gases have volume. There's nothing you can do to like reduce the volume. There's nothing you can do. So what can you do, guys? I mean, so what you can do with the volume is what? Okay, use a gas that is what, guys? That has a small volume, such as helium or what? Hydrogen. These guys have what? They're very small gas particles, okay? I mean, they're small gas particles, also what? They have a very weak IMF as well, okay? So yeah, like, okay, so one way is what, guys? Yeah, use a gas that is what? Small volume, that's one way, okay? But still, it will deviate. Like, dude, like, they got volume too. There's no question. If you smash in a lot of H2 gas in the container, of course, they will take the volume. So what do you do, guys? So what's the best way to do so? You might want to have a container that's what? At a low pressure. So what does it mean by low pressure, guys? So low pressure means what, guys? Low pressure means there are not many gases exerting pressure. There's not many gases in the container. So which means what? You have a very large container and what? Very small amount of gases in there. Okay? So like, dude, think about it, guys. 100-liter container, you have like 5 HE gases. Okay? So does it really matter how, like, 5 helium gases? Does it matter how much of the helium gas takes up the volume? It doesn't. Okay, so yeah, so which means low pressure. Okay, if the pressure is low for the gases, and if you select the gas with a low volume, okay, then yeah, they relatively follow the real and ideal gas pathways. Okay, so these are something that you can do. Okay, low pressure, select the gas with the low volume, make the temperature high. Okay, and also what? Select the gas with the small IMF. But then what? Yeah, the real gas perhaps deviates less from the ideal gas equation. Okay, so that's one of that. Dude, this is like your like Regents level chemistry they teach you. They teach you this. You gotta know it. Okay, you should already know this. If you have taken chem before. If you've never heard, like I don't know, but This is not AP. This is like what you should already know, okay? But now, with the AP, okay, you have to take it to next step. They will ask you harder questions about this, no question asked, okay? So, first thing first, guys, you have to know something called Van der Waals equation, which deals with the deviation of the real gas and ideal gases. So this is where I tell you, okay, this is the hardest part of the AP, like gas chapter, by the way, the deviations. I mean, they sometimes ask, sometimes don't. It's the hardest part if they do ask. So, and the kids don't understand, like, they're like, what? Like, all right, so take a look at this. So, so keep in mind, guys, okay? You gotta have one understanding. Okay, look at this. For real gases, real gas versus ideal gas. Okay, yeah, real gases, okay, always have a lower pressure. Real gases always have lower pressure than ideal gases. Okay, they always have lower pressure. Why? Why do you think the real gas was? So what I'm saying is this, okay? Based on that PV&RT equation, okay? So dude, like, okay, so based on PV&RT equation, right? PV&RT, which is ideal gas law. You expect the pressure to be 1 atm. Oh yeah, based on the volume, based on number of moles I added, the temperature, I expect the pressure to be 1 atm. Okay, so 1 atm, because I added volume, whatever the volume is, and blah, 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 I expect the pressure to be 1 atm. Pressure is always lower than what you anticipate. Yeah, why? Why is pressure lower? Dude, this is the question you begin on the AP. Like, you gotta explain, oh, why is my pressure low? Pressure is lower than the ideal gas. Because why, guys? Real gases have what? This is just like I explained. Real gases have what? They have IMF. They have internal moving forces. Regardless of like what the hell the gas is, they have IMF. Which means what, guys? So I think last year when I was sitting and arguing with this, I mean, like I was like, what are you guys talking about? So keep in mind, every time there's no question, okay? The real gas pressure is less than the ideal gas pressure. The reason is, think about it, guys. The gas must collide into wall to exert pressure. Okay, they gotta hit it, exert force, bounces back. That's how the pressure is exerted, okay? But the problem is what, guys? When they are colliding, there's other gas here that what? Attracts it, pulls away. So it must hit with a certain force, but because there's what? Other gas particles in there, what happens, guys? It reduces the force of the collision, which means what? Like, dude, I'm about to hit the wall, okay? But there's someone pulling me, okay? Which I'm gonna hit the wall softer. That's what's happening. That's IMF right there. So when this guy is hitting the wall, there's a guy attracting this guy, which means what? It softened the pressure or the force when this guy hits the wall because of the IMF. But there's no question there, guys. IMF will reduce the force of the collision and what? Lowers the pressure of the real gases. There's no question there. Okay, so that's one. Pressure is always lower. So now we got to think about the volume. So this is a volume, guys, is where this is the tricky one. Okay, we got to discuss the volume. Listen very carefully to this one, guys. You know, this is where it gets a little bit tricky for the volume of the ideal gas versus the real gases. So now, yeah, take a look at this, and like don't forget, guys, okay, with the volume stuff. Let's say, guys, yeah, so catch. Okay, so whatever that is. They usually don't live in a carpet because their legs gets caught up. Whatever. So I'll take a look and if it goes near you. Alright, guys, let's take a look at the volume. So yeah, let's.
I can't end here.
What up?
I can't end.
What? And?
Yeah.
It's okay. Alright, guys. Let's take a look at the volume. So yeah, let's take a look at this. I have 1 liter container, 1 liter, okay? And the gas that I added, the particles of gas, right? This is a container volume, right? I added the gas particles, okay? The gas particles took up 0.1 liters, 1 liter, okay? So I have a 1 liter container, the particles volume is 0.1 liters. You know what I'm saying? So whatever the gas that I put in, guys, it took up 0.1 liter. Okay? So now look at this. So now I want to solve the equation PVnRT. So per ideal gas understanding, the volume should be the container volume of 1 liters, right? Which means I'm going to put 1 liter in the equation. Okay? But now, if the gas took up 0.1 liter out of 1 liter, so whatever that I put in, guys, they took up the volume. The gases took up the volume of the container. What should I put in? What should be the volume? What should be the volume that I should put in the equation, guys? What do you think? I have to subtract this volume minus what? 1. Which means what? I gotta subtract 1 minus 0.1 what? 0.9 liters should be the volume that I put in. Okay, you gotta subtract the gas molecule's volume it took up of the container. And then that should be in the volume of the gas. Okay? So that's a deviation also as well. So, which means what, guys? The real gas volume should be what, guys? You gotta subtract the gas particle of the volume, okay, in order to what? Get a proper reading. Okay, so you know. So, which means, guys, okay, the van der Waals equation corrects the deviation and give the equation for this. So I forgot exactly what the equation represents. Okay, it should be the reading, guys. I'm going to provide to you guys. Okay, take a look at this, guys. Okay, so the equation goes in terms of van der Waals equation. The pressure, yeah, look at this pressure of the real gas pressure that you get, plus a certain value, K. So keep in mind the equation is what? PVnRT, right? P times V equals to nRT. So you have to add, because the pressure of a real gas is always less than the pressure of ideal. You have to add a certain value, a constant value, to make it into a pressure of ideal. Because why? It's always less. Okay? And now you have to subtract a certain value. So this is a pressure, this is the volume of the container. You gotta subtract the volume of a real gas, how much gas you added in, from the container volume in order to correct for what? Deviation for the real gas versus the ideal. I tell you, man, like, this is the hardest part to understand, and you gotta understand what the hell I'm doing here, okay? So I'm adding something to the real gas pressure. You're supposed to get 1 atm, but when you measure it, it becomes what? Like 0.8. So you gotta add something there to compensate for the lower pressure value. And then I'm gonna what? The volume of the container minus what? How much gas particles I have to correct for what, guys? The gas particles volume. And then I can what? Get what? The equation that's properly needed for the real gas perspective. So your teacher or even the AP, they will not make you calculate stuff using van der Waals equation, but they will be asking stuff like this, okay? So, oh yeah, based on my calculation, the pressure came out to be less than what's expected. Why? They'll ask the question. You go, oh yeah, IMF. So something like that will be asked on the AP, guys, which means it will be a scope where it's beyond what you learned on the topics that you guys know. And like for the regular Chem, yeah? For any questions, I mean, I don't know, we're crazy guys right now, give you questions on this, but let me know any questions or concerns, let me know on the van der Waals. But you gotta know it, guys. Okay, so it's not something that, oh yeah, you don't have to know, you don't have to know, it's fine. I can't do it because you definitely have to know this for the AP. Questions, let me know. Questions, concerns on this? Yeah. Okay. So the one piece, guys, so after I go over this, I'm gonna take a look at the homework, guys. So I don't know if I can finish, but let's see. So the other piece, guys, that I want to talk about, other than this, and again, like if you think like, oh yeah, I don't get some part, like you gotta stop me because I will not know, guys, what's in your head, okay? Like you gotta, like I can't read your mind, guys. You guys, if you don't know, guys, stop me and let me know, okay? All right, so the other piece, guys, you have to know is it's this one. It deals with stuff that we've done today, which is the bonding and the phase change. Okay. So we got something about vapor pressure. Okay. This one has a little bit of bonding stuff in it, also for the gases as well. Okay. Let's understand, okay, what vapor pressure is. Okay, what it is and what the hell do you have to know about this, and how does this have any relation with the bonding? So guys, let's take a look. Very, very important, guys. Pay attention, please, on this one, okay? So whatever, like, you know, like some of the stuff, I mean, everything I put on the board, guys, it's on the AP, okay? So I don't know if you're a school teacher, it varies by your school, guys, by the way, so I don't know what the hell your teacher's gonna do. Some of them I know, some of them I'm not sure. Some of them go above and beyond, some of them, like, I don't care, you know, teach you stuff. But these are some of the stuff that's on the AP, guys, yeah? So I can only attest to, you know, what's on the AP, guys, yeah? So now, let's take a look. So we have a liquid here. Okay, so whatever the liquid it is, guys, X, substance X, liquid. So look at this, guys. Once we discuss a liquid, what happens, guys? This is not ideal. Okay? So based on an ideal gas, there shouldn't be any liquid at all. Okay? But once we talk about there's a liquid, what happens, guys? Dude, this is what? Non-ideal. Okay? The real stuff, okay? So now, one thing that we talked about as well. Okay, so at temperature 25 degrees Celsius, at temperature 25 degrees Celsius, what happens, guys? Yeah, like the basic equation that we know, average kinetic energy equals what, guys? 3/2 times RT. So at a certain temperature, they have some sort of what? Kinetic energy. They move around, because we know. So we talked about it, guys. This equation is what, guys? This is what, guys? Universal. It doesn't apply for gases only. Applies for liquid or solid, whatever, okay? So at temperature 25, what happens, guys? Yeah, dude, okay. They have some kinetic energy. They move around, okay? As even for a liquid. So now, keep in mind, listen very carefully now. This is called the average. We're not saying kinetic energy. We're saying what? Average kinetic energy. Okay, what does it mean, guys? At a certain temperature, which is 25 degrees Celsius, on average, there's a kinetic energy, but not every particles of the X have the same speed. They, on average, that's what they get, but, you know, like not every particles have the same speed. So, now listen very carefully. This is on the AP a lot of times. It's called a Boltzmann's diagram, okay? Whatever, Boltzmann diagram, okay? You've seen the reading. So, listen very carefully, okay? This represents, so on the bottom represents the kinetic energy distribution, okay? This represents number of particles. So at a temperature 25 degrees Celsius, how would the distribution look like? Okay? So at temperature 25 means, dude, it's an average, right? Like, okay, so what's the distribution? So it's a bell curve, like this. So keep in mind, so what I can tell you is this, okay? In terms of understanding of this, guys, by the way, it's a number of individuals versus someone's height in a population, okay? Like, dude, on average, okay, like US, like height, I don't know what the average height is, right? So it's what? It's a bell curve. Some of them are tall, some of them are short, like most of them falls into what? The average category, right? Like, dude, oh yeah, the average height for US is like, 5'9", okay, for male. Like, does it mean like everyone has a 5'9" height, guys? That's not true, right? Some of them are taller, some of them are shorter. Like on average, it's what, like 5'9", whatever, okay? So you can understand, guys, right? Same thing, okay? Average kinetic energy at a certain temperature value. Temperature 25, it's what? It's a bell curve. Some of them move really fast, some of them move really slow. But average-wise, that's what it is. That's what this graph represents. That's what we call, guys, a Boltzmann's diagram. They have this question a lot. The diagram, like, dude, they have a lot of these stuff in the AP. So now, keep in mind, guys, when temperature goes up, what happens, guys? When temperature increases, average increases as well. How would this graph be any different, guys? It'd be what? Yeah, it'd be shift to the right. You know what I'm saying? Okay? So this is what? When temperature is 25 is this. This is what temperature is when it's 50%, okay? There's more particles at greater speed, and that's why the graph shifts, okay? So they have, dude, I tell you, man, like, a lot of these guys are in there, okay, on your AP exam. So that's called the Boltzmann's diagram. So now, why I'm saying this is this, okay? At temperature 25, okay, some of these guys move fast, some of them move slow, some of them are here, whatever, they're all over the place, okay? So, you know. But now, yeah, what about the ones that are moving really fast? These guys. What do you guys know about these guys? What can happen to these guys? Fast moving particles near the surface. What do you think, guys? They can break the intermolecular forces and what? Turns into what? Into a gas. Keep in mind, guys. What makes them a liquid is what, guys? IMF. Okay? And what happens, guys? Okay, so if you move fast, if you like move really fast, what happens, guys? You can break the IMF and what turns into gas. Okay? So once these gases, yeah, think about it, once it turns into gas, what happens, guys? They exert container pressure. Okay? So what do we call this, guys? We call this what? They call this vapor pressure. Okay? So when some of the particles that are moving really fast at a certain speed, okay, they turn into a gas, and dude, like what you guys should know, when they turn into gas, what happens, guys? They exert pressure. A simple way is what? They call that what? A vapor pressure of a substance X. Okay, so I will not discuss right now equilibrium vapor pressure right now. Okay? I'm not gonna go equilibrium right now, but again, that's how the vapor pressure is being exerted. But now, like one of the questions that you had on the homework, right? So what decides the vapor pressure? Like why some of them have a high pressure, some of them have a low pressure? Like that's where the question was becoming, right? Like some of the stuff you have to know. So now, let's take a look at these two containers. Let's say, guys, this is X is water, H2O. This is what, guys? I'm gonna say this is an alcohol or acetone, liquid. So now they are at the same temperature. Water, acetone. Acetone is what, guys? Like what? Nail polish remover, guys? That's acetone. So yeah, based on your knowledge, right? Which one vaporizes easily? Which one? Of course the acetone, right? Like, dude, if you put it on your hand, what happens, guys? Turns to gas right away, right? So let's take a look. Let's take a look at the Boltzmann's diagram for water and also for acetone. So guys, this is the number of particles. This is kinetic energy, okay? So now, for water, I have the diagram like this. Right? Dude, like, this is the, okay? That's for water, H2O. Temperature 25 degrees Celsius. That's for H2O. Yeah, what about for acetone? Yeah, what about for this guy? What do you think? So, same temperature, relatively same amount of acetone, for example, guys, right now. What do you think, guys? Keep in mind, guys, the equation that we know, average kinetic energy, 3/2 RT, this is what? Regardless of what substance it is, you give the same temperature, same kinetic energy. Which is what, guys? Yeah, same line. Acetone have what? Same line. There's no difference there. They have the, because why? On average, on same temperature, they have the same kinetic energy. But now, what do you know? Yeah, H2O, they have hydrogen bonding. Acetone, what happens, guys? They have no hydrogen bonding, okay? So which means what, guys? They have a stronger IMF, they have a weaker IMF. These guys are holding on to each other what? Strongly. Which means what, guys? So for water, you need to have more than this much energy to what? This is the amount of energy needed for them to turn into a gas. Okay, that's the threshold kinetic energy for what? Water to turn into a gas. So a very few of them can turn into gas at temperature 25. Okay? What about this guy? Acetone, what do you think, guys? So they have a weaker IMF, which means what, guys? More particles can turn into a gas at a lower temperature. Because why? They have weaker intermolecular force of attractions. You understand, guys? So, which means what, guys? What's going on here? So, based on the understanding, what's going on, guys? If you have weaker IMF, what happens, guys? Yeah, think about it. There's more particles turning to gas, which results in what, guys? Greater vapor pressure. You need to understand this, okay? So you know. So weaker IMF, stronger or greater vapor pressure. Because why? More of the gas particles are what? Turned into a gas. Okay? It's, dude, like this is yeah, like some of the classic questions they have on the AP, okay? Any questions, guys? So I will not go to the boiling point, guys, by the way. So boiling point, guys, that's something that we'll take care of, guys, later. But keep in mind, guys, that's something that you've probably seen on your homework, guys, by the way. You know, like, oh yeah, like they talk about the IMF, they talk about the vapor pressure, you know, like, okay, like what the hell vapor pressure? So I understand some of the questions on the homework you've seen, 47 questions. I mean, there's some here, which I understand. Some of the questions about the heat, So I figure like if you've done like not everything right, that's fine, okay? But just have understanding what's going on, guys. Boltzmann's diagram to understand what it is. And also, guys, when temperature goes up, what happens, guys? This graph will shift. Which is more of the particles can be what? Turned into a gas. Okay, which means the vapor pressure goes up. So when temperature goes up, the vapor pressure goes up because what? More of them will get turned to gas, exert to greater pressure. Okay, and that's what you understand about the vapor pressure. How it relates to the intermolecular forces, by the way. Okay. Any questions, let me know, guys. Questions, concerns about this? Let me know, guys. The vapor pressure stuff. Any questions, concerns? Let me know. All right, guys. Let's take a look at it. So I'm not really 100% on this one, guys, but let's take a look at your homework, guys. Like, go to your homework, guys. So I'm gonna start recording.